Good afternoon, everyone. Good evening, good morning, depending on where are you from. My name is Marcin Kosinski. I'm a volunteer at YR Foundation. Today, I have a pleasure to guest Hedia from Our Lady's Tunis, who will be our host, and Paul Buerkner, who is our great speaker for tonight. At the beginning, I would like to ask everyone on the audience to say where are you all from on the chat. Next to the video, there's a chat where you can post all the questions and comments that we will use during the Q&A at the end. This webinar will take 40 minutes. At the end, we will have Q&A session with Paul. We are really happy to have Hedia and Paul here as we are trying to be really remote and support various local R communities around the world. And that wouldn't happen without the support of our sponsor, Jumping Rivers, which is an analytics company that provides consultancy and various R courses. So starting from that point, I would like to give my microphone to Hedia so that we can get an introduction of our speaker.
Thank you, Marcin. So I'm really happy to introduce Paul Buerkner. Paul is a statistician currently working as an independent senior research group leader at the Cluster of Excellence SimTech at the University of Stuttgart, Germany. He is also the author of the famous R package brms and member of the STAN development team. Previously, Paul studied psychology and mathematics at the University of Münster and Hagen, Germany. And he did his PhD in Münster about optimal design and Bayesian data analysis. He has also worked as a postdoctoral researcher at the Department of Computer Science at Aalto University, Finland. Thank you, Paul, for being with us today. The screen is yours.
Hello, hello everybody. Thank you very much for inviting me. Thank you very much for the introduction. So I'm going to share my screen, and so I suppose you can share my screen. Great. So today I want to talk about an introduction to Bayesian multi-level modeling with my R package, brms. And I don't know what it is about kind of Bayesian statistics and Bayesian statisticians that they always have the feeling that they need to start with a Bayes theorem. So that's what I'm going to do as well. So in Bayesian statistics, when we're doing Bayesian inference, we're interested in the posterior distribution. That is the probability distribution of the parameters theta given the data y. Well, and we compute that by multiplying the likelihood with the prior distribution. So the likelihood, the probability distribution of y given theta is basically the probability distribution through which the data informs the parameters. And it's basically what we also optimize in classical statistics. But in Bayesian statistics, we have a second component called the prior, which provides information about the parameters that doesn't come from the prior, but from that doesn't come from the data, but perhaps like from expert knowledge or from other sources of information. So in Bayesian statistics, we're combining the information from the data with other information sources, and that jointly informs our parameters. And then basically we use that posterior distribution to make inference. And the way I would like to think about Bayesian statistics or Bayesian inference is a little bit differently, in that I just like get rid of this normalization constant that I had in the denominator that I don't want to talk about today, and just think about the posterior distribution as being proportional to the product of likelihood and prior, which is then nothing else than one factorization of the joint distribution of the data and of our parameters. Or we can also think about the right-hand side, this probability distribution of y and theta, as being the joint distributions, a distribution of all variables we have in our model, some of which are known or observed, we call that data, some of which are kind of unknown, we call that parameters, but ultimately it's just all of our variables that are jointly in one distribution. And we just hope that our structure of our joint distribution and the amount of known variables is sufficient so we get helpful and reasonable inference about our unknown variables, that is of our parameters. And that's how I really think about Bayesian modeling, is that we put everything together in a joint model and that hope we have enough information in it so that we get something reasonable out of it. And there are lots of ways where you can do Bayesian statistics and do Bayesian inference. And one way to do Bayesian inference on your data is to use probabilistic programming language Stan and my BRMS R package that I want to talk about today. And so here I just want to list a few advantages and disadvantages of Bayesian statistics. That is my personal list. You may have other advantages and disadvantages. This is just how I feel about it. So in Bayesian statistics, one advantage for me is that we have a natural approach to expressing uncertainty, which is using probability distributions and generally probability. That is, all the uncertainty in our data, in our parameters, perhaps even in our models, is expressed through probability, which I think is intuitive. We have the ability to incorporate prior information, for instance, expert knowledge in our models, but we don't have to. That is, we can also choose not to use that kind of prior information and only specify weakly informative priors that basically don't add much information to the models. We have increased modeling flexibility. That is, we are able to estimate much more complicated models with much more parameters, often much more parameters than we have data, and still get reasonable inference out of that through these advanced estimation techniques. We get the full posterior distribution of parameters. That is, we not only get a point estimate and some approximate measure of uncertainty, but we have the full distribution of the parameters in the form usually of posterior draws, that is of random draws from our distribution. And that also enables us the natural propagation of uncertainty. That is, when we're doing Bayesian statistics, we not only get a posterior distribution of the original parameters, but we get posterior distributions of all quantities that can be theoretically computed based on these parameters. That is, suppose we have parameters A and B, then we also get the posterior distribution of A plus B, or A divided by B, or A to the power of B if we wanted to, or something like more complex like posterior predictions, for example. So when we do Bayesian inference, we not only get the posterior distribution, but all posterior distributions of push forward quantities we can compute on that basis, which I think is a really nice and powerful property that I regularly use automatically in Bayesian statistics. And that basically I assume when you're using Bayesian statistics, you will find useful as well. So there remains one disadvantage is quite a big one, is that estimating Bayesian models is really slow. So when you're used to kind of fitting your classical frequentist models in a second or under a second, or perhaps like 3 seconds, in Bayesian statistics, it may take 20 seconds. If it's really quick, it may take minutes, hours, or even days, right? If you have really big models. So usual full-based Bayesian estimation is orders of magnitude slower than kind of classical counterparts. So you really have to get used to waiting longer for your models. For example, you could use that time to fight on Twitter about Bayesian fragmented statistics, or you can drink more coffee or whatever. In any case, you have to get used to that, at least when you want to run full Bayesian estimation on your models. We're actively working on improving the speed of model estimation in Bayesian statistics, but it fundamentally remains a hard problem, and it fundamentally remains slower in almost all cases than classical optimization-based techniques. So the way I prefer doing Bayesian inference and Bayesian analysis is through the probabilistic programming language Stan. So Stan is a programming language just as R, Python, Julia, whatever you're using, but it's focused on writing probabilistic models, that is, writing Bayesian models. And it's a library written in C++, but comes with its own nice language to kind of intuitively write those models. At least I find that intuitive. And it has some very powerful sampling algorithms, most notably Hamiltonian Monte Carlo and some more advanced Hamiltonian Monte Carlo versions, so to speak. And it runs on all major platforms. That is, it runs on Mac, it runs on Linux, it runs on Windows, and it has interfaces to R, to Python, to Julia, whatever you are using. So I'm not going to talk about Stan in detail today, but I want to show you quickly how the syntax looks so that you get an impression of how that works. Right, so that's a Stan syntax for linear regression. It's just like one potential example. So the Stan language is written in blocks, and there are 3 main blocks. There are a little bit more, but 3 main blocks. Data, this is where all your knowns go into. parameters, that is your unknown variables that you want to infer, and the model block where you put everything together, that is put the data together with the parameters, specify likelihood and prior, and then when you run the STAN model based on your data, in the end, inference will come out. So for example, in this linear regression case, what kind of data are we needing? So first of all, we need kind of an integer of length 1 that basically tells us how many observations we have. I call that n in this case, and it's an integer, and we need to have at least one observation, otherwise linear regression wouldn't make sense. Then we have a response variable, I call that y, it's a vector of length n. Then we have kind of a number of regression coefficients we want to estimate, I call that k, again, we need at least one regression coefficient. And then we have kind of a predictor design matrix that contains our predictor variables or features in machine learning language as columns, and rows are kind of the information for each individual observation. And this is a matrix with n rows and k columns. So what you already see here is that STAN is statically typed. That is, you have to define the type of every variable you're using beforehand. So it's not adapted to the data, but rather you need to fix the type, and then the data need to be consistent with the type you're specifying, which makes it, of course, like a little bit harder to write because you need to think of all the types. But the advantage is that you can read STAN syntax if you're used to it, and you can read the models of other people and understand quite well what those models are doing if the code is nicely written, even if you haven't seen the specific data that other people may use that model on. In the parameters block, what we need for linear regression is we need a vector of length k of regression coefficients. I call that vector b for regression coefficients. And then we have like some additional parameter, which I call sigma, is the residual standard deviation of the likelihood, and it's a real value with a lower bound of 0. So instead, it's important that you specify those boundaries because sigma is supposed to be a standard deviation. It cannot be negative, so you need to tell STAN that there's a hard boundary at 0 so that it kind of takes that into account. Finally, in the model block, we put everything together. So we're defining a linear predictor vector, which I call mu, and mu is simply the matrix product of x, our design matrix, times the regression coefficients b. We can specify a prior. For example, we can say that sigma should have an exponential prior with rate 0.1, if that was appropriate for our data. And then we finally also specify the likelihood and say y, that is the response variable, is normally distributed with this mean linear predictor vector mu and the residual standard deviation sigma. Right? So this is kind of just in a nutshell some basic STAN syntax. Of course, this becomes much more complicated for more complicated models. And hence I've developed a higher level interface to STAN, which I called brms. And it's an R package that makes kind of using STAN easy from R, at least I believe. It makes it easy. So we are specifying models, that is Bayesian models in STAN using extended R formula syntax. So if you're familiar with LM or GLM functions or the LMER or GLMER functions in R, then you can also use brms more or less right away. And what brms does, it internally writes STAN code that is readable, human readable, yet fast. So whenever there's a trade-off between readability and efficiency, I'm going with efficiency. So I'm trying to make brms models really efficient for the given data and model structure, but I try to make the STAN code as readable as possible. That is, if you want to learn STAN from brms, you can still try to do so. And I know a lot of people who have been doing it like that. I provide an easy interface for defining price in brms, and I also facilitate post-processing. That is, all the summarization, plotting, predictions, model comparisons, model selection, variable selection, all that kind of stuff you want to do after fitting your model or multiple models is automated in brms, and you have methods for that, so you don't have to reinvent the wheel and build everything from scratch, every model. If you're using brms, all the post-processing functions are already there for you and ready to use. So what happens brms behind the scenes when you were writing the STAN code? So let's take a look at some semi-complex multi-level model that I will also use later on, how that looks in STAN language when brms writes it. no worries, we're not going to discuss that in detail. I just want to show what happened. So after you specify some semi-complicated model, BRMS kind of writes the stand code for you, has data blocks and transformed data, that is data that is computed based on data passed by the user. Then we specify a bunch of parameters. Then we specify like a lot of stuff in the model block, computing the likelihood, computing priors, and then we generate also some quantities. The point is not to go into the details here, but just to show you there's a lot of stuff happening behind the scenes. If you're specifying the same model in Stan yourself, chances are your Stan code would look much more kind of simpler and more readable, but BRMS uses this kind of writing the models, first of all, to make it generic enough, to make it efficient enough, and also like using some numeric tricks that increase, for example, numerical stability, but also sampling stability and efficiency. Okay, but we don't have to worry about Stan today. We're going to worry about BRMS. So I want to talk about a few things that matter to me when I'm analyzing data in general, but specifically with BRMS. So the first thing I want to talk about is that we should think about the data structure when analyzing our data and when building models that fit to our data. And the example I want to use is kind of a famous example of effects of sleep deprivation on reaction times. It's called the sleep study data set, which is stored in the LME4 package in R. And so here we have data of 18 subjects about the effect of sleep deprivation on reaction time. That is, after initial day of kind of regular sleep, they only get 3 hours of sleep maximum per night for 9 consecutive nights. And then we see how the reaction time, like in a simple reaction time task, develops over those consecutive days of sleep deprivation. And what we clearly see here is that there's lots of differences between different subjects. So for instance, the subject on the top left kind of starts at 250 milliseconds and then has quite a lot of increase in average reaction time over the days, while kind of the next subject here starts quite quickly and basically isn't affected by sleep deprivation at all. So there's not only lots of differences between individuals, but we can also explicitly model these differences. And the way that connects to the question that we should think of the data structure is that we know we have multiple observations per individual or subjects here in this example. And this knowledge of the data structure, of having this nested structure in our data, time points and individuals, is something we want to take into account in our model. That is, we want to, in this case, use multi-level models to fit that data. So we need to think of what kind of data structure we're having and then use that data structure to explicitly build the structure into our model so that the model can account for the uncertainty on different levels, hierarchical levels, for example, in our data. So we can run kind of Bayesian regression models, multi-level regression models, for example, and we can get kind of individual lines of fit, regression lines for each individual subject. And we clearly see there's lots of variation in those regression lines between subjects. But before we kind of run a multi-level model, let's just run a very basic, very simple linear regression model in BRMS. We can do that. I mean, usually you want to fit more complicated models, but we can do the very simple models in BRMS as well. So the single interface to modeling in BRMS is the BRM function. And it uses our formula syntax, that is the response variable. Reaction is on the left-hand side in this case of the tilde, and our only predictor days of sleep deprivation is on the right-hand side of the tilde. So reaction is predicted by days. And the data set we're using is going to be the sleep study data set. So we specify the model in BRMS, we run Stan behind the scenes, and then we can use lots of post-processing methods, for example, conditional effects to kind of plot some conditional predictions and that show us kind of the prediction lines between the predictors and the response variable. And so here we see kind of an average effect of days over the subject on the reaction time, right? So that's nice and good, and we see reaction time increases as people like get little sleep. But like we didn't really take into account the structure of the data. That is, we didn't take into account that we had actually multiple observations per subject. So we need to have that data, that structure in the model in some way. So what we're going to do is we specify a multi-level model in BRMS. And the formula now gets a little bit more complicated. So we are still predicting reaction times. We're having an intercept, which we had before, just implicit. We have an overall effect of days. And here, more importantly, we have some more terms, which is a varying intercept over subject and a varying effect of days over subject. That is kind of not only do we assume that there's an overall effect of days on the reaction time, but this effect varies over subject. The starting point, the intercept varies over subject, and the effect of sleep deprivation varies as well. And the syntax, some kind of predictor terms, this pipe symbol subject is also the syntax in the LME4 package, specify kind of predictor terms varying by the grouping structure. In this case, the grouping structure is subject. Then we're going to fit the model, and then we again, for example, could plot conditional effects and see that now this is the overall regression line of the prediction of days on reaction time. And what we see here is that in comparison to the former case with just linear regression is that the uncertainty has increased quite a lot. And that's good because that model took into account the multi-level structure in the data. So as a result, the uncertainty estimates are more reasonable. They are more conservative and they're more appropriate for the data at hand because the data contains the multi-level structure. It contains this uncertainty. So we want to model it. And this is kind of the result we get, higher uncertainty, which is the correct way of modeling it because this uncertainty is actually in the data because subjects vary from another. So we had thought about the data structure. Let's think about distributions. And in Bayesian statistics, kind of everything has a distribution because everything is expressed, or every uncertainty is expressed using probability. So we really need to think about distributions everywhere. One place where we're going to think about the distribution is the likelihood, that is the probability distribution of the data given the parameters. And here I'm using another example. It's the kidney data set. So we're predicting the time until reinfection with a kidney disease, and we're predicting it by age and sex of the patients. And so let's assume we didn't think about how this time variable would be distributed, and we just would assume it has a Gaussian distribution, that is, it has a Gaussian likelihood. Of course, it doesn't really make sense because kind of time until reinfection, it's time, it can only be positive. But the Gaussian, the normal distribution doesn't know that. So we may run into trouble, which is indeed what happens. So here I'm kind of showing you a posterior predictive check plot, PP check plot. And the dark blue line is the marginal cumulative distribution function of the observed response, Y, that is kind of the time until reinfection. And those light blue lines are posterior predictions of the model. In other words, those light blue lines tell us what kind of data would the model predict. And it's kind of a minimal requirement. We would expect, or we would hope that at least marginally, as we've shown here in the plot, that the models predict the data well in the sense that those light blue lines are similar to the dark blue lines, at least here in this case, marginally. That doesn't mean the model is great, if that's the case, but certainly the model is quite bad, has some problems at least if those lines don't match. And what we see here specifically in this case is that because the Gaussian distribution doesn't know that time can only be positive, the Gaussian distribution also predicts negative time values here in the lower part of that plot, which clearly is not sensible. So this model, although it kind of may be reasonable in other cases, has like really bad predictions because we didn't think about the distributions well enough. In this case, we didn't think about the likelihood. So let's change our likelihood and use kind of a gamma distribution with a log link. We specify the same model. And when we now look at the posterior predictive checks, we see that the posterior predictive lines, the light blue lines, really nicely overlaying the observed data, which means kind of, in this case, at least marginally, the gamma distribution, the gamma model does a much better job in fitting this data appropriately, because the gamma distribution can only take on positive values, which is naturally for this kind of time response variable. So thinking about the likelihood makes sense, because then you can get not only good predictions as shown here, but you also have a better chance of kind of getting valid estimates and valid inference from such a model. But we should also think about the prior. That is, we should think about the distribution of the parameters before seeing the model. And that's actually not super simple. So let's take the same example and let's think about the prior. For example, we could say we specify a normal prior with mean 0 and standard deviation 0.5 on our regression coefficients. This is kind of the third line here. We're using the prior argument in BRMS to do so. And since we just want to look right now, what kind of predictions would the model make if it hadn't seen the data, but only had the prior? We're setting sample priors only. That is, we're going to fit the model or run the model only on the prior and not on the data. And as a result, when we run posterior predictive checks, we get actually prior predictive checks. That is, what kind of data would the model predict if it just knows the prior but not the data? And it turns out when we do those kind of prior predictive checks, things are really difficult in lots of cases. So here on the x-axis, we see the log of the observed responses, y, and on the y-axis, we see the log of the predicted responses based on the prior predictions of the model. And we see here we're about kind of 10 orders, or like one order of magnitude 4 versus 45 away from our predictions. So our prior predictions are completely nonsense in this case. And that basically tells us that our priors were kind of completely nonsense and way too wide, because the model based on the prior just predicted way too big responses. The specific reason in this case is that age is kind of in years, which is a quite big scale. And we also were using a log link, so our predictions get exponentiated. And when we then specify a comparably wide prior for that predictor with a really big range and exponentiate it, our predictions explode. Which means is if we are interested in specifying informative priors, which we specifically should be interested in when our data isn't informative enough, we should really think carefully of how to specify priors. And BRMS provides us with all the tools, for example, prior predictive checks, to do so, to specify reasonable priors for our model parameters. I just want to kind of use that time to talk about one specific feature, which is like a special case of kind of a more general feature in BRMS that allows to add additional response information to the model. For example, in this case, it's censoring. So the time until reinfection turns out to be actually censored because some participants or some patients are fortunate enough to not have a reinfection until the end of the study. In other words, they may have a reinfection after the study at some point, but certainly not until the end of the study. And so this implies kind of a censoring aspect of the model, which we need to take into account in our model to do kind of correct inference. And the way these response addition terms are specified in BRMS is that on the left-hand side of the tilde of the formula, you are specifying your response variable, you're using this pipe operator, and then afterwards you're adding kind of additional information functions, for example, the sense function that indicates censoring, and it takes one variable. In this data set, it was called censored with the censoring information, and you can use kind of right censored, left censored, and even interval censored if you want to. And there are some more addition terms for weighting, known standard errors, some other information if you need to, that all add information to the response variable, but are not technically the response variable itself. And this is how you enter that in BRMS. Okay, so another feature I want to talk about is the modeling of unknown nonlinear functions. So suppose you have a response variable y still, and you have a predictor variable x, but you don't know how the function relationship of those two variables is. What you can specify only is that y is probably equal to some function of f plus some error term epsilon. The problem I'm running into in a lot of cases, and you probably also run into, is that you suspect this f is somehow nonlinear, but you have no idea how that nonlinear function looks like. So you need the model to find out by itself how this function f looks like. And BRMS has multiple ways to accomplish that, most notably splines and Gaussian processes. So what we do in splines, in a nutshell, is that we say that our f of x is the sum of some basis function bj multiplied by some basis function coefficients beta j. And those bj's are kind of flexible enough. And if we add enough of these basis functions together, each having their own basis function coefficient beta j, then we can approximate a lot of highly complex nonlinear functions using this approach. Of course, there's a danger when we do that we're overfitting the data, because easily our model becomes too complicated because we have so many potential parameters if our j is pretty large. So what I do in BRMS and a lot of other packages in R do as well, they're not just using splines, they're using penalized splines. And in Bayesian statistics, penalized splines just means we put a joint distribution over our basis coefficients beta j. So we assume that those betas are all coming from a joint distribution with some hyperparameters lambda. And by doing so, if we do that in the right way, we at least can try, and usually we succeed to prevent overfitting. Splines are quite technical, and I don't claim I understand all details of it. Fortunately, in the BRMS interface, it's very simple to set up splines. So if you want to use a spline to predict y by x, you specify just y tilde s of x, and then you're going to be fitting a spline on x to predict y with some reasonable default options, and you can specify all the options you want using this s function. Of course, you can add a lot of other predictor terms, multi-level predictor terms, whatever you're interested in. Unknown nonlinear functions are Gaussian processes. So that technically, we assume that this kind of nonlinear function f of x is a infinite dimensional normal distribution, usually with mean 0 and some covariance kernel or some like covariance matrix. And we can use that even if we have finite data to specify some highly complex nonlinear function. Again, you don't have to worry about most of the details, because in BRMS you can just say y is predicted by a GP, by a Gaussian process of x. But be careful, Gaussian processes, at least the exact ones that are like shown here, are really slow. So if in doubt, perhaps start with splines and only use GPs if you know what you're doing, or you're using some approximate GPs, which are also implemented in BRMS, and you can specify the kind of approximation in the GP function in BRMS if you want to. So I want to use splines now in a little bit more complicated example to predict the housing rents in Munich. So what we're going to do, we're going to predict the rent per square meter of an apartment by the area of the apartment and the construction year of the building the apartment is in. And what is more, since we have different districts in Munich, some of which are expensive and some of which are really expensive, we also want to kind of take that into account using a varying intercept. The problem here is that we have literally no idea how the area of the apartment and the construction year relates to the rent per square meter. So what we're going to do is we specify a two-dimensional spline of area and construction year, and we're adding the varying intercept of district. Then we're going to fit the model, and it just like runs, I don't know, half an hour or so, perhaps less, perhaps it takes a little bit longer depending on how quick your laptop is. And then we can get results, which I'm going to show in a second. But what you can now also do in BRMS is we can not only predict the mean of the likelihood, the mean of the response distribution, but we can also predict auxiliary quantities, auxiliary parameters of the response distribution. For example, in Gaussian models, the residual standard deviation sigma. So for example, in some districts, there may be more variation between observations than in others. And if those variation is not explained by the model, it remains as variation in our residuals. And this is something we want to take into account. That is, BRMS allows for distributional regression, where you not only predict the mean, but all parameters of your likelihood. In this case, because that's the kind of a normal likelihood, the residual standard deviation sigma. So we're going to predict the mean of rent per square meter by area and construction year. And also the residual standard deviation sigma is predicted by a spline of area and construction year, again with a varying intercept. And I've added another feature here to this model, which is instead of one pipe, I used two pipes and wrote D in the middle. So the symbol D doesn't mean anything here. You could literally write something else. The point is here that this D is the same for both terms. And in BRMS, if you specify multi-level or like varying terms that way with some common symbol, they are going to be modeled as correlated even across formulas. Usually you want your varying effects to be correlated, and the way you make them correlated across formulas in BRMS is by using two pipes and specifying a symbol between them or multiple symbols, right? You could literally write pipe, I don't like to wait for my Bayesian model that long, pipe, and it would work as long as kind of the same symbol is used between the pipes. Okay, we're going to fit that model. We wait a little longer yet again because it's a more complex one. And then we can again plot predictions, or in this case, we are plotting the smooth terms, that is, we are plotting the splines. So here I have the spline, the two-dimensional spline as a kind of a surface plot looking at it from above of the prediction of mu, that is the prediction of the mean rent per square meter. And more brighter values are indicating higher rent per square meter. And what we see here is that the average rent per square meter is particularly high for very young buildings, that is very kind of young construction years, near 2000 in this case, and very small apartments. And this is the place we have really high rent per square meter, while for quite old buildings and quite big apartments, the rent per square meter is comparably small. Comparably, again, because it's still mean. And now we have kind of also fitted a spline for the residual standard deviation sigma. And what we see here when we look at this plot is that the residual standard deviation, that is the variation in the apartments with construction, with a certain construction year and certain area, is specifically big in very small buildings, very small old buildings on the bottom left, and also specifically big on like very large buildings that are very old at the same time, while there are places kind of on average kind of area between like 80 and 100 square meters that have been built in the 1970s, where there is kind of very little variation in rent per square meter across the apartments. So we have seen here that we can not only predict the mean, we can also predict the standard deviation, and we can do so using unknown nonlinear functions just estimated from the data, for example, splines. I'm going to quickly talk about just like one thing before coming to an end, which is we also want to do model comparison. And one way to do model comparison is to run cross-validation of the models. Without going into the technical details here, what we're doing with cross-validation is we're splitting our data into subsets. One we call training data, that is the data we fit our model on, and the other is our test data that is used to evaluate the out-of-sample predictive performance of our model. And we don't do this kind of split just once, because then our predictions would just be very dependent on our training test data split, but we do that a lot of times. And when we do a lot of times this training test data split, we call it cross-validation. The problem is in Bayesian settings of doing cross-validation is fitting one Bayesian model is already quite slow in comparison. So if you now suddenly fit 100 or 1000 models, it becomes like really slow if your initial model was already slow. So we have kind of developed ways to do approximate Bayesian cross-validation that just usually works on the complete model and approximates a cross-validation procedure without actually having to refit the model. And one such kind of approximate cross-validation procedure is called approximate leave one out cross-validation, where in this case, each time we're leaving out only a single observation, fitting the model on all other observations, and then predicting that one observation. And we do that for each observation in the data. And because the difference, so to speak, of the full model with the model without that one single observation is quite small, this is something we can approximate, in this case, approximate using importance sampling. So we use this kind of Loo method on it, and it runs approximately Buerkner cross-validation quite quickly, usually in a couple of seconds, without requiring any refits, just working on the full model. So we can do that for our two rent models that I showed a couple of slides ago. And then we can compare the two models with each other based on Buerkner cross-validation. What we see here when running Loo compare in this case is that the first row always indicates the best model, and we are always comparing all models with the best model. That is because in the first row, we're comparing the best model to the best model. The difference and the standard error of the difference to the best model is 0. And then in the consecutive rows, we see kind of the other models. And here, when we see in this kind of plot that the fit rent 1, that is the one without actually predicting sigma, is around minus 51 ELPD values smaller, whatever those ELPD values are for now, with a standard error of that ELPD difference of 10.6. So if we want to do a rough approximation, the difference is about 5 standard errors away from 0, which is usually quite substantial. Like, at least that's a short explanation. And so in this case, we would be quite sure that at least when we look at Buerkner cross-validation performance, the model not only predicting the mean, but also predicting the residual standard deviation actually is better. I'm going to skip that case study so to come to an end soon. So if you want to learn more about me, I have a website. You can write me an email. You can tag me on Twitter. If you want to learn about BRMS, which is probably more likely, BRMS has a GitHub page. You can ask questions on the Discord Stan forum. You can look at the extensive help page inside R from BRMS, and you can look at like a lot of different vignettes that I've written about BRMS. There are also lots of tutorials and blog posts out there on the internet about BRMS. So there are lots of resources where you can learn about it. If you want to learn more about Stan, you can look at Stan's website, and you can also visit the Stan discourse forums. So it's been a pleasure to be here, and thank you very much for listening, and I'm now happy to take questions.
Thank you, Paul. Thank you very much for this amazing talk. So we have 8 questions. The first one is, how do you initiate and convince people about the Bayesian approach?
I don't really convince people. Usually people have modeling problems that they don't know how to tackle. And one way or the other, they usually arrive at the conclusion, or perhaps Bayesian statistics would be a potential solution. So they kind of run into BRMS and they try to fit it. Sometimes it works, sometimes it doesn't, and then they tend to ask questions. So usually I'm not the one motivating them. It's more like that their problems are motivating them to try different approaches because the standard approaches don't work. And then a lot of people actually ending up with Bayesian approaches because those tend to work in kind of a lot of more complex statistical modeling problems than classical models, at least in my experience.
Thank you very much. So the second question is, do we need to know any Stan to use BRMS?
No, you don't have to. So you can kind of extract the generated Stan code if you're interested in, but you don't ever have to worry about Stan when you're using BRMS. The only thing you need to make sure is that you need to have a C++ compiler so that basically Stan can compile its models at runtime, but there are kind of detailed tutorials and explanation of how to get a C++ compiler running on your system. And these days, unless you have very specific versions of Mac, it's quite simple to get that to work.
Great. Maybe I'll take the third question, Paul. Thanks for the talk. There was a good introduction, but also there were advanced parts. So questions are also on an advanced level. So forgive me if I don't fully understand the scope of the question, but there was one question about BRMS support for matrix structures. And the specific use case is whether BRMS supports matrix structures that are there so that the random effects can be specified for the model and residual variance matrices can be computed. Is that the use case for BRMS? Do you have any experience with that?
So I need to look at the details. So of course, there are a lot of different ways how you can think of what a metric structure could mean literally. So what BRMS allows is, for example, if you have kind of a random effect structure and you know the correlation between the random effects that happens, for example, in biology, where you have phylogenetic structure, phylogenetic correlation matrices. This is something BRMS allows, so you can specify those known correlation matrices. I have no idea if that tackles the question. So if you have specific question of specific modeling, I think it's best that you ask on Stand Discourse, detailing your question, and then people may be able to help and point you in the right direction. So perhaps it's BRMS, but I can't speak for certain because there are so many different ways where you can use matrices potentially.
Yes, and I would say that's a great advantage of R and open source, that you can solve multiple questions, but yeah, you need to try various approaches. Thanks, Paul. Maybe Hader, you will take another question.
Yeah, thank you.
Yeah. Oh.
So the other question is, does BRMS uses non-centered parameterization?
So the question was if BRMS uses non-centered parameterization?
Yes.
Yes, sort of to give a little bit of detail. So we can write kind of varying effects, varying intercepts, varying slopes in different ways. And one is kind of centered, that is specifying a prior directly on those varying effects. And one is called non-centered, which means we're specifying a prior on some scaled varying effects. And then after specifying the prior, we scale it. It's centered and non-centered is super a misnomer, because in both cases it's centered around something. Just non-centered means centered around 0 initially. So yes, BRMS only uses non-centered parameterization, and the reason it is because numerically and computationally more stable in 98% of the cases. So BRMS uses non-centered parameterization throughout.
Okay, so maybe I'll have a follow-up on that. Is it sometimes better to have this non-centered parameterization because of the computation advantages, even though the model specification looks weirder because of that you need to have transformed parameters?
So it is almost always better from a statistical and estimation point of view to use non-centered parameterization. And so if like once you got used to kind of looking at non-centered parameterization in Stan, it doesn't hurt too much anymore. But in most cases, and actually almost all cases I've seen, non-centered was much better. And like they are very simple model where like centered parameterization already falls apart super heavily, but there are some special cases that I can't name right now, but I know they exist and I've seen them where centered parameterization is better, but that is rarely the case. So it's almost always when you write your models in Stan yourself, worth it to use non-centered parameterization.
Okay, thanks for the explanation. During your talk, there was a wide conversation about confidence intervals and credible intervals. So the question originated in the chat was, is it possible to get confidence intervals? But from the conversation, we saw that there is an actual difference in the approach when it comes to Bayesian statistics and frequentist statistics. But as an expert, could you like briefly explain what is the difference between credible interval and confidence interval, and why frequentists would like to get confidence intervals, and that's probably not the thing that you can get with Bayesian statistics?
Mm-hmm. Yes. So so confidence intervals and kind of credible intervals, as one example for Bayesian confidence, for Bayesian uncertainty intervals, differ in what kind of uncertainty they're quantifying. So confidence intervals quantify the uncertainty under repetition of the same experiment. So technically, if we think about a true parameter and we have a 95% confidence interval, in infinite or like very large number of repetition of that example, 95% of the confidence intervals will include the true parameter. In the sense, it's kind of the probability comes from repetition of the same, or repeatability of the same experiment. While in Bayesian statistics, our uncertainty intervals could be credible intervals, could be, for example, highest density intervals. They're quantifying the uncertainty of that specific data, of that specific experiment, because they're quantifying the kind of uncertainty we have based on our data and our prior knowledge. That is, if we have a 95% credible interval, we can say with 95% probability, based on our data, based on our model, based on our priors, I expect my parameter to be in this interval. This is not something I can philosophically say with confidence intervals, because confidence intervals are only defined when I'm able to repeat the same experiment. Well, the Bayesian uncertainty intervals can work directly on one specific data, one specific model, because they're quantifying my uncertainty using probability, not the repeatability of an event. So this is philosophically, right? In practice, I can use credible intervals I can use them to satisfy frequentist criteria. That is, I can use kind of credible intervals, Bayesian uncertainty intervals, and see if they have kind of a 5% rejection rate of some sort of parameter under certain cases, which are usually of interest in the frequentist statistics. But I have no kind of guarantee that a Bayesian credible interval is kind of nicely calibrated in a frequentist way. Conversely, I can interpret confidence intervals as credible intervals under very specific assumptions. When I kind of specify completely flat priors, then there are special cases where confidence intervals and credible intervals overlap, or like are the same rather, or very similar. So there are philosophical differences. There are special cases where they overlap, but ultimately it depends on what you're interested in, right? So if you're interested in frequentist criteria, it doesn't mean necessarily that you want to run frequentist statistics. You could also use credible or uncertainty intervals in Bayesian statistics to satisfy your frequentist criteria, right? But in any case, what works and what doesn't work, and in which cases depends on the criteria you're interested in. And you can use both intervals for both kind of ways to interpret your uncertainty and whatever criteria you have, but there's no guarantee that they will work as you expect. That was a long answer, I know. And there are lots of more details to it. So just to add one more thing, lots of analysis I'm doing, I'm kind of using Bayesian models to satisfy frequentist criteria. But I'm using Bayesian models because they are in more complex analysis settings, they actually far better in satisfying my frequentist criteria than the frequentist models, specifically when I don't have any software, don't have any implementation of such kind of complex models and frequentist statistics. And even if I had, it will probably not work out well, for example, without prior information.
Mm-hmm. Thanks, Paul. That was very extended, and I'm glad we have you here and we are recording, because next time there will be exams from statistics. We can just send this video to all the students and they will know the difference between those types of criteria and intervals. Awesome. You know, there's one a bit complicated to say because that's a maths formula, but I will try to do my best. So is it possible to model y against x, where actually x isn't in the linear form, but it's kind of like it's included in the tangent function multiplied by some constant. So this is not directly the linear model, but there's some like function that is put on x.
Mm-hmm. Yes, I think I get it. Yes, you can do that. So I assume that you don't. I assume that in this question, the person asking that had a specific functional form in mind. And this is what you can do in BRMS with kind of an explicit nonlinear modeling, where you specify your nonlinear function literally, and then you tell BRMS that this is a nonlinear function, please take it literally, and then estimate your nonlinear parameters. So I don't have a good way to communicate that now, but if you look at the BRMS formula function in BRMS, or short BF function, there you'll have kind of like lots of documentation that will also tell you how you specify those explicit nonlinear functional forms in BRMS.
Okay, great. BF, that's the function that will help. Hedia, would you like to pick some next questions?
Yes, thank you, Martin. So the question is, do you mostly use brms or SAN in your research?
Can you repeat, please?
Do you mostly use brms or SAN in your research, like R or SAN?
I'm sorry, I didn't quite understand the question.
I can repeat. Do you use BRMS or stan in your research?
It was an or, yes. So basically I can answer yes. I use both. So most of the stuff I'm doing can be specified in BRMS directly, and some more complicated stuff that I'm writing my own Stan code. So basically I'm my most frequent user, I guess, in BRMS. So I frequently do that. And it helps me a lot in further developing BRMS because I kind of see what I need for analysis, and it turns out to be that a lot of other people also need that as well.
Thank you. So the other question is if you created BRMS first, or if you were part of the STAN development team first.
Mm-hmm. Yes. So I was a little PhD student, just working on some ordinal models and ordinal multi-level models, and I couldn't fit them in other probabilistic programming languages like JAX or Winbugs. So it's like writing my models in Stan, and then to make things more usable, I kind of wrote some R wrapper around that, and then I continuously added upon that. I was just like a little PhD student, didn't have nothing to do with Stan, and I just kind of created BRMS, and eventually it became so successful that I was invited together with BRMS to kind of become part of the Stan team.
So you have 3 remaining questions. Are there any plans to incorporate GLM into BRMS? Something like multi-level Bayesian structural time series?
So some of such like multi-level Bayesian structural time series models may be possible. So BRMS has time series support, for example, using kind of autoregressive moving average structures, something like that. At some point, BRMS had some like simple correlation structure that was called Bayesian structural time series models. I suppose it's what is asked, but like I don't know the details right now. The reason I removed that at some point was that it didn't quite fit into the rest of the structure and is quite hard to estimate. So depending on what kind of model you are having in mind, it may be possible. You may need to check the documentation. You may ask on the Stan forums, but there are also other more specialized R packages that are using Stan behind the scenes. And I also know that multiple of those are actually doing time series modeling. So there are quite good chances that you find some Stan-based R packages on the internet that are able to run these models without you having to specify them in Stan directly, even if BRMS turns out not to be that kind of package.
Okay, I think I can take a few last and we can call it a day. Thanks for being so patient, Paul.
Always.
So one of the question is, okay, I think I'm gonna ask that question. So we had Jose on the audience who was very eager and explained a lot of Bayesian statistics while you were talking, and he was also very involved in answering questions. And he has a question whether you would like to be interviewed in the Learning by Stats podcast.
I don't know that podcast, but why not? Feel free to contact me, and I'm happy to figure out kind of if I can contribute something there. Yes.
Yeah, Jose. So there is a URL to Paul's website under the video. He said yes, so just get him in contact. And I also have a personal question. So you mentioned that you were struggling with some Bayesian statistics while you were a PhD student, and you used JAX and Winbugs. Mm-hmm. That sounds ancient. Wasn't Stan popular at that time, or it was just this research group, or why did you try those languages? Were those the one recommended by the community at that time? How did it happen that you started with those languages and then you moved to Stan? How did the community react to your approaches on your own to Stan, and then how did they receive you using R? Yeah, so I think the main point was that when I was doing that kind of stuff, I wasn't even a Bayesian statistician, right? I've been doing lots of optimal experiment design from like fragmentist perspective in my PhD apart from BRMS.
So I wasn't experienced at all. So I just like used what I had like read about earlier in the book. And so I think Stan was, I think, started being a thing 2011, but I may be wrong. I don't know the exact time. I was started working on BRMS in 2015. And back then, for example, RStan, the main R interface to Stan wasn't even on cron. And so I think it wasn't, I mean, it was probably like a lot of people knew it already, but it was not as easily usable as it is now. It has evolved a lot and has gotten a lot of traction in recent years. And turns actually out that like I put BRMS on cron before RStan was actually there. So in the early days, people had to download stuff from GitHub to get it to run. So nowadays things are much easier in a way. So I think it was just my ignorance that like made me use other languages, although in psychology, they were for a long time much more popular. And I think Stan has like in lots of places taken over in some sense, although I can't speak for the larger community. And there are lots of models, to be honest, that kind of other languages are perhaps even better. So I don't want to claim that Stan is uniformly better than languages, even if the other languages are older.
I see. Thanks. I didn't know that BRMS was before RStan on cron, so good to know. And we're happy to have you in our community. I hope that in the future you will be as successful programmer as you are currently. Paul, this is the end of the sessions that we have. And yeah, we used your time and energy already. So we are really thankful that we had you here. And just as a last sentence, we keep having those webinars every week. So if you are on the audience interested in joining other meetings, please have a look on our list on our YouTube channel and see what we have prepared for next weeks. And if you have any last famous words, Paul or Hedia, that's the time.
So I would just to quickly thank Hedia and Marcin for having me here, and the audience for listening to my rambling about Bayesian statistics. And I hope to see you in the future, perhaps in person at some conference, at some event, when things are like back to normal. Again, thank you very much for listening.
Yes, thank you very much for this amazing webinar, Marcin. So very nice. Thank you.
Alrighty, let's call it a day. Thanks for joining. See you next week. The same